Isomorphic graphs and their representations. First off, isomorphic graphs. Basically, an isomorphic graph is one that looks exactly the same and acts exactly the same as another. In this case, G1 and G2 are isomorphic. If you recall earlier, I mentioned that the distance between edges and the orientation of vertices doesn't make a difference as long as the connections between them are the same. So we can see that here, A, B, C, D, E, and F have been arranged now in a clockwise manner. And the edges, though, have been preserved. So it's the exact same edges connecting the different vertices on G2 as on G1. Thus, these two graphs are isomorphic. The precise definition, of course, is much more complicated. Doesn't make... it's not too much more complicated. Basically, it states that there has to be a function between vertices that takes this, each vertex in G1 to a vertex in G2 that is injective, so the function must be one-to-one, and it must preserve the connections. So the edges between those vertices must correspond as well. That's basically all it means for two graphs to be isomorphic, but simply the connections must be the same and the vertices must correspond. Of course, I could rename each of these vertices and these would still be isomorphic graphs. Okay. Right here, excuse me, is an adjacency list. Adjacency list. It's exactly as it sounds, which we have vertices on the left. Every possible vertex is listed on the left, and all the adjacent vertices to that vertex are listed next to it. So, adjacent to the vertex A, we have the vertex B, E, and F. Adjacent to B, we have the vertices A and C. Adjacent to C, I know it's kind of hard to see, we have B, D, E, and F, and so on. So each connection is listed here, not as an edge, but rather as an adjacent vertex. So if we're sitting at vertex C, which other vertices can we go to? We can go to F, E, D, and B. Those are listed as the adjacent vertices. So that's an adjacency list, not too complicated. Oftentimes, we can represent that, well, I shouldn't say oftentimes, but we can always represent it as a matrix. However, if we have a lot of vertices, then the matrix can be, a lot of edges, so lots of vertices and lots of edges. This list can get quite long, quite complicated, and a little more difficult to follow in the long run. So we can create an adjacency matrix. In which we have each vertex, for each vertex has a row and a column corresponding to it. In this case, I have 6 vertices, so I've got 6 rows and 6 columns. Oops, A, B, C, D, E, and F. And then to create our adjacency matrix, the entry in the matrix will have a 1 if there's a connection between those matrices, those vertices. So we'll put a 1 here if we can go to A from A. Okay, in other words, there has to be a loop in order to put a 1 in basically this entire diagonal. Since there's no loops in our graph G1, the entire diagonal is going to be filled with zeros. The only way we can get a 1 as an entry in our adjacency matrix is by having a connection between those two vertices. There is a connection between A and B, so we can denote that. Of course, because this is an undirected graph, any 1s that go in this upper triangle are going to go in the lower triangle as well, and the same with zeros. So we're going to have a correspondence across this main diagonal for an undirected graph. We'll talk about a directed graph briefly in a moment, but there is not a connection between A and C. You can look here. I've already said that these are isomorphic. In fact, they're the same graphs. And over here, both of which show that there is not a connection between A and C, so we get a 0. B, however, is connected to C, so we get a 1 there. And just continue this process. D is only connected to C, so we can put a 0 in every, corresponding to every vertex except C. So that one's fairly quick. And we just continue this process until the entire matrix is filled in. Of course, it's going to be a little confusing to look at from our standpoint, but the obvious connections to computers will make it a lot simpler to be used in the long run. So A to E, there is a connection. A is also connected to F. E and B is not connected. Oh, it is connected. E is connected to B. B is not connected to F. E and C are connected. F and C are connected. F and E are not. Okay. So, adjacency matrix follows pretty quickly from the adjacency list, or from the matrix itself. I'm sorry, the vertex graph itself. Whichever you want to follow, it doesn't matter. But this isn't the only matrix we're going to use. We will be discussing an incidence matrix. So with an adjacency matrix, we have vertices as the rows and columns. With an incidence matrix, we will have vertices as the rows, or representing the rows, and edges representing the columns. So we can discuss which vertices are touched by or connected to which, incident with which edge. Okay. The obvious downside to an incidence matrix is if there's a lot of edges, particularly if your graph is not simple, so we have 2, 3, 4, 10 edges between different vertices, then an incidence matrix can get extremely complicated. Whereas with an adjacency matrix, if we were to go from our simple graph here and add in some extra rows, some extra edges like those two, we simply represent it down here by, well, this is connecting A and B. Now there's 1, 2, 3 different edges. So instead of a 1 there, we'll put a 3. That's all that changes. And again, if we have 2 connections between B and C now, instead of a 1 between B and C, we have a 2, and so on. So it's very easy with an adjacency matrix to show multiple edges, whereas with an incidence matrix, you have to represent each of those edges as a column. It can get quite long and quite tedious. Now with the directed graph, again, these are undirected graphs. With the directed graph, not much changes. But with our adjacency list, we'll have an initial vertex column and terminal vertex column. And with the adjacency matrix, then we have initial vertices, terminal vertices. And you put a 1 in that entry if there is an initial vertex to a terminal vertex for that particular, those two particular vertices, or an edge between those with initial and terminal vertex. The only way the adjacency matrix will change with a directed graph is instead of having this similarity between the upper and lower triangles, it may be different because we have initial vertices here, terminal vertices here. So we may have, say, 3 edges that go from B to A, but no edges that go from A to B. So this might be a 0, and this might still be a 3 with a directed graph. That's the only way it would change. Not much else would change with that. So not too exciting there, not too complicated either. These are just representations for graphs, and what we'll do later is use these representations, or what we can show is using these representations, namely matrices, to determine whether or not 2 graphs are isomorphic. Now for an incidence matrix, not much changes. It's the exact same procedure, only with our incidence matrix. You can see all I've done is taken G1 and relabeled it with edge numbers, E1 through 7. With the matrix, all the changes is we get a 1 as the entry if, say, edge 1 is incident with connected to vertex A. Then we'll put a 1 in that entry, a 0 otherwise. Okay. Of course, with an incidence matrix, we're just talking about particular edges, so this has nothing to do, or I'm sorry, there will never be more than a 1 or a 0 in any of these entries. Whereas with a non-simple adjacency matrix, you can get a 3, 4, 5, however many edges connect those given vertices. You can get that as an entry, those larger numbers. That's not possible here because we've got each edge denoted by its own row, or sorry, its own column. Of course, that also means that if you have a lot of edges, this is probably not the best method to demonstrate how the graph is connected. Okay. But we can fill it in. Again, we get a 1 in this as this entry if edge 1 is connected incident with vertex A. E1 is indeed connected to A, so we get that, and we could just go straight across row by row. Perhaps be a little bit easier in this case. A is connected with E1, E5, and E7. 1, 5, and 7, and it'll be 0 everywhere else. B is incident with edges 1 and 2, 0 everywhere else. C is incident with E2, 3, 4, and 6, 2, 3, 4, and 6, 0 elsewhere. D is only incident with edge 3. E is incident with 4 and 5. So we denote those, put zeros elsewhere, and so on. So an incidence matrix, not too complicated, not too exciting either, to be honest. But it can be helpful in determining if your function is an isomorphism. Now, back to isomorphisms. An isomorphism itself is a function which is one-to-one between vertex sets of two different graphs. I guess it could be the same graph. Two graphs. So an injective function between two graphs which preserves connections, essentially. Two graphs are isomorphic if there exists an isomorphism. Between them. So, like we've seen before, this comes down to just proving whether or not this function exists. Oftentimes it's easiest to show that two graphs are not isomorphic solely because you don't have to find that particular, remember there exists, so we don't have to find that particular or a function that is an isomorphism. If we can simply show that two graphs, for example, don't have the same number of vertices, then they're not isomorphic. If they don't have the same number of edges, they're not isomorphic. So those are two quick ways to show that two graphs are not isomorphic. Again, not isomorphic if different number of edges, or vertices. So one quick way, different number of edges or vertices. Also, degrees of particular vertices. For example, if G1 has V such that the degree of V is 5, and G2 has a maximum degree of 3 for all edges. It's another way to show pretty quickly that those two graphs are not isomorphic. This one comes up in surprising places, so it is just one to keep in mind. Other ways to show that two graphs are not isomorphic is to show that there's a property that one graph has that the other graph does not. This is an example of one of those properties, that is a vertex of degree 5, which the other one does not have any vertex over degree 3. In general, again, that's showing that G1 has a graph invariant property. That G2 does not. I apologize, I'm running out of space. Graph invariant property that G2 does not. I'm not going to go into too much detail as I do in the book. I think going into too many variables can get a little confusing, especially with all the different superscripts and subscripts involved. But basically, if we want to show that G1 is isomorphic to G2, we first need to find a function f, injective, which will send a vertex in G1 to a vertex in G2. And of course it has to be injective, so it can send a vertex over here to exactly one vertex over here. If G2, for example, had more vertices or less vertices than G1, obviously we can show that it's not isomorphic pretty quickly. So we're assuming they have the same number of vertices, and we can find this function that sends something in G1 to G2. Oftentimes, these are not, these are not functions like f of x equals 2x plus 3. Not those kind of functions. Okay. These are functions more in our notation, as we've seen before, and the book denotes it that way as well. F of v1 is u3, f of v2 is u1, and f of v3 is u2. So it gets a little tedious to define such a function, but the point is we need to be able to find that function. Okay? We don't have to find the particular function in order to prove an isomorphism, but that's about the quickest way by definition to show that two functions are in fact isomorphic. So we can find this injective function And then, using F, we show that the incidence matrices, adjacency matrices, and or adjacency lists are the same. But again, you have to be using that function f in order to show that. If you're not using the function f, if you haven't sent v1 to u3 and so on, then there's a chance that you could still have an isomorphism between G1 and G2, or those could be isomorphic, but your matrices, these adjacency and incidence matrices or the adjacency lists, would not be the same. Okay, so you have to use F in order to do so. Now, where we go from here, we will be using these representations in the future, only slightly. For the most part, we're going to be discussing other properties of graphs and kind of going away from these isomorphisms and the representations themselves. So this section and then the problems in the back of this section are mostly just for your sake and getting some work, in creating these adjacency lists, adjacency matrices or incidence matrices. But we will be seeing these in the future.